Right now, while you're listening to this, a piece of metal no larger than a compact car is screaming through the pitch-black silence of space at 34,000 miles per hour, more than 13 billion miles away from Earth. It is powered by 3 decaying spheres of radioactive plutonium that produce less electrical energy than a standard kitchen microwave. Its radio transmitter radiates a signal so unimaginably weak that by the time it reaches our planet, the energy harvested by our massive ground dishes is less than a fraction of a billionth of a watt, a signal a billion times fainter than a digital wristwatch battery. Yet that fragile ancient machine, launched before the personal computer was even invented, is doing something that has broken our fundamental understanding of interstellar physics. For decades, theoretical astrophysicists predicted that the edge of our solar system was a gentle, gradual transition zone. Standard textbooks taught us that the sun's protective magnetic bubble simply thinned out until it merged smoothly with the cold, empty vacuum between the stars. Science calculated that Voyager 2 would drift peacefully into a low-density, quiet cosmic void. Standard physics was dead wrong. When NASA redirected Voyager 2, thrusting it downward through the completely uncharted southern hemisphere of our cosmic bubble, the probe sent back telemetry that left the world's top astrophysicists speechless. It did not find a quiet vacuum. It struck a violent, ultradense magnetic wall, a boundary burning at tens of thousands of degrees that defied decades of mathematical modeling. Before we dive into the data, hit subscribe to join our community of space enthusiasts, and drop a comment below letting me know which city or country you're watching from today. To understand the true magnitude of what Voyager 2 transmitted back from the edge of the abyss, we have to travel back to a time when humanity first dared to dream of throwing a message in a bottle across the ocean of interstellar space. The story begins in the late 1960s, when a brilliant young mathematician named Gary Flandreau made a startling discovery while working at NASA's Jet Propulsion Laboratory. Flandreau realized that in the late 1970s, a rare celestial alignment was going to occur, an alignment that happens only once every 176 years. The 4 outer planets, Jupiter, Saturn, Uranus, and Neptune, were going to sweep into a single geometric arc on the same side of the Sun. This alignment presented a once-in-a-lifetime opportunity. By firing a spacecraft toward Jupiter, mission planners could use the giant planet's immense gravitational well as an orbital slingshot. The spacecraft would steal a fraction of Jupiter's orbital momentum, boosting its velocity and bending its trajectory towards Saturn. Saturn would then fling it toward Uranus, and Uranus would hurl it toward Neptune. Without this gravitational assistance, a trip to the outermost planets would have taken nearly 30 years using the chemical rocket technology of the time. With the Grand Tour alignment, it could be accomplished in little more than a decade. NASA Mission Control executed an ambitious plan, constructing twin spacecraft, Voyager 1 and Voyager 2. Voyager 2 actually launched first, lifting off from Cape Canaveral atop a massive Titan IIIe Centaur rocket on August 20th, 1977. Voyager 1 launched 16 days later on a faster, more aggressive trajectory. Voyager 2 was built as the ultimate planetary insurance policy. If Voyager 1 failed its primary objective, a high-risk flyby of Saturn's moon Titan, engineers were prepared to redirect Voyager 2, sacrificing any chance of visiting Uranus and Neptune. Voyager 1 succeeded flawlessly. Titan was mapped, its dense nitrogen atmosphere confirmed, and its trajectory was bent upwards, sending Voyager 1 shooting out of the ecliptic plane into the northern region of the solar system. That single success unlocked Voyager 2's legendary destiny. NASA Mission Control executed a precise trajectory correction maneuver, locking Voyager 2 onto a path that would take it to all 4 giant planets, a feat that remains unrepeated in human history. Voyager 2 reached Jupiter in July 1979, capturing stunning images of the Great Red Spot and a revealing active volcanism on the moon Io. In August 1981, it swept past Saturn, braving the complex ring structure and measuring atmospheric winds exceeding 1,000 miles per hour. In January 1986, it arrived at Uranus, discovering 11 new moons and measuring a bizarre magnetic field that was tilted 60 degrees away from the planet's rotational axis. And in August 1989, Voyager 2 made its dramatic encounter with Neptune, discovering the Great Dark Spot and capturing geysers erupting on the frozen surface of Triton. That was a success, but the planetary flybys were only Chapter 1. As Voyager 2 completed its final planetary encounter at Neptune, scientists executed a crucial maneuver. By skimming over Neptune's north pole, the planet's gravity acted as a downward slingshot, redirecting Voyager 2 out of the ecliptic plane and plunging it downward into the uncharted southern celestial hemisphere. Computer models at the time suggested that this trajectory would take Voyager 2 through a quiet, uninteresting zone of space. Astrophysicists expected the solar wind to gently decay until the spacecraft floated into the interstellar medium without much fanfare. They calculated that interstellar space was homogeneous, cold, and dark. They did not expect the boundary to fight back. To understand what Voyager 2 encountered out there, you first have to understand the invisible cosmic structure that we live inside. Our sun is not just a ball of light, it is a violent nuclear engine that constantly exhales a supersonic gale of charged particles outward in every direction. This stream of solar plasma travels at speeds between 200 and 800 kilometers per second, blowing outward into the void. As this solar wind expands into space, it carves out a gigantic protective cavity in galactic space known as the heliosphere. The heliosphere is our cosmic house. It encompasses all 8 planets, the asteroid belt, the Kuiper belt, and extends billions of miles into the deep dark. Think about what that actually means for a second. Beyond our heliosphere lies the interstellar medium, the turbulent ocean of galactic gas, dust, magnetic fields, and high-energy radiation generated by exploding stars across millions of years. Where the expanding solar wind collides with this interstellar ocean, a physical conflict takes place. Here's how to picture it. Imagine a powerful garden hose turned on inside a deep swimming pool. Around the nozzle, the jet of water pushes back the surrounding pool water, carving out a clear, churning pocket of air and water bubbles. That air pocket is the heliosphere. The heavy pool water trying to crush back inward is the interstellar medium. The boundary line where the force of the air jet balances the crushing pressure of the surrounding pool water is the heliopause. For decades, we had no way of measuring that boundary directly. We only had theoretical calculations. But on November 5th, 2018, at a distance of 11.9 billion miles from the Sun, nearly 120 times the distance between the Earth and the Sun, Voyager 2 reached the line. Unlike Voyager 1, whose primary plasma science instrument suffered a fatal hardware failure back in 1980, Voyager 2 was carrying a fully functional plasma science instrument known as the PLS. The PLS consisted of 4 cup-shaped sensors called Faraday cups, designed to measure the density, speed, temperature, and direction of charged particles. For the first time in human history, an operational set of electronic eyes was crossing the physical border of our solar system, while directly recording the density and movement of interstellar matter. On that November day, telemetry streams flowing into NASA's deep space network suddenly spiked. Not a metaphor, not a technicality. The readings on Voyager 2 registered a violent, instantaneous change. Within a span of hours, the solar wind particles, which had surrounded Voyager 2 for 41 years, dropped to almost zero. Simultaneously, the instrument detected a massive spike in high-energy galactic cosmic rays coming from deep space. The plasma density jumped by a factor of more than 20. Voyager 2 had punched through the heliopause and entered the interstellar ocean. When astrophysicists analyzed the raw telemetry and published their peer-reviewed findings in the journal Nature Astronomy, the academic world was rocked. The data disproved virtually every established theoretical model of our solar system's outer boundary. First, the heliopause was far sharper, thinner, and more rigid than anyone had predicted. It wasn't a murky, blurred zone of transition. It was a crisp, highly defined cosmic barrier where solar plasma and galactic material slam into each other under immense pressure. Second, and far more shocking, was the plasma temperature reading. Standard solar physics assumed that as a spacecraft moves further away from the radiant warmth of the Sun, space would become progressively colder, eventually settling near absolute zero. Instead, Voyager 2's Faraday cups revealed that the plasma directly outside the heliopause was burning at a staggering 30,000 to 50,000 Kelvin. That is roughly 50,000 to 90,000 degrees Fahrenheit, several times hotter than the surface of the Sun itself. Think about that number for a moment. Voyager 2 was moving through a wall of fire. How could a spacecraft made of aluminum, titanium, and copper survive floating through a region of space burning at 50,000 degrees without instantly melting into a puddle of slag? The answer lies in the subtle difference between heat and temperature in a cosmic vacuum. Temperature is a measure of how fast individual particles, ions and electrons, are moving. In the interstellar medium outside the heliopause, those charged particles are moving at tremendous speeds, which yields an exceptionally high thermal temperature. However, heat transfer requires mass. It requires particles physically bumping into an object to transfer their kinetic energy. The interstellar plasma, while superheated, is extraordinarily diffuse. There are only a few particles per cubic centimeter. Here is how to picture it. Imagine sticking your hand into a hot oven set to 400 degrees Fahrenheit. You can keep your hand in the hot air for several seconds without getting burned, because the air molecules are spread out and transfer heat slowly. But if you touch the metal oven rack at that same temperature, your skin burns instantly because the metal is dense and transfers energy rapidly. The space around Voyager 2 is like an oven filled with almost no air at all. The individual particles are screaming fast, but there are so few of them colliding with the spacecraft that they cannot transfer enough heat to warm up the metal hull. In fact, because Voyager 2 radiates its own internal heat into the void, the physical body of the spacecraft remains bitterly cold, hovering near absolute zero, even while floating through an ultra-hot plasma shield. And here is the part nobody is talking about. Voyager 2 revealed that the interstellar magnetic field outside our solar system does not tilt or warp away as predicted. Instead, it runs almost perfectly parallel to the magnetic field inside our solar system. This magnetic alignment creates an extraordinarily tough, pressurized magnetic wall that repels interstellar cosmic debris. Furthermore, Voyager 2 discovered a previously unknown boundary layer just outside the heliopause, a region where interstellar plasma stacks up against our heliosphere like water pushing against the bow of an icebreaker ship. Our solar system is not just drifting quietly through the Milky Way, it is plowing through a superheated, highly magnetized interstellar storm at 45,000 miles per hour. Gathering these miraculous measurements is one thing, but extracting those numbers from a machine built in the early 1970s and transmitting them across billions of miles of empty space is an engineering triumph that borders on magic. The technological reality of Voyager 2 is mind-boggling. The spacecraft does not have a modern microprocessor. Its central computer system operates on roughly 68 kilobytes of total memory. To put that in perspective, a single digital photograph taken on a modern smartphone takes up about 3 to 5 megabytes, meaning a single photo contains roughly 50 times more data than the entire onboard computing capacity of Voyager 2. Voyager 2 stores its data on a physical 8-track magnetic tape recorder. When the tape fills up, the computer rewinds it and plays it back to the radio transmitter, streaming bits of data across the void at an agonizing rate of just 160 bits per second. Communication with Voyager 2 is constrained by the speed of light. As of 2026, Voyager 2 is more than 143 astronomical units, over 13.3 billion miles from Earth. When mission controllers at NASA's Jet Propulsion Laboratory in Pasadena, California, send a radio command to Voyager 2, that signal travels through space at 186,282 miles per second. Yet because of the immense distance, it takes roughly 19.5 hours for the radio beam to reach the spacecraft. Engineers then have to wait another 19.5 hours for Voyager 2's high-gain antenna to transmit a response back. Every single command cycle is a nerve-wracking 39-hour waiting game. If engineers send a faulty line of code, they won't know if they bricked the spacecraft until almost 2 days later. Worse, the spacecraft's power source is dying. Voyager 2 does not use solar panels. At 13 billion miles from the sun, solar radiation is too weak to generate electricity. Instead, it relies on 3 radioisotope thermoelectric generators, or RTGs. These RTGs contain pellets of plutonium-238. As the plutonium naturally undergoes radioactive decay, it generates heat, which thermocouple junctions convert into electrical power. Plutonium-238 has a half-life of 87.7 years. Every single year, radioactive decay combined with the gradual degradation of the thermocouples strips away approximately 4 watts of power from the spacecraft. At launch in 1977, the RTGs produced 470 watts of electricity. Today, that power budget has dropped by more than half, leaving the spacecraft running on a razor-thin electrical margin. In recent years, this dwindling power budget triggered a series of life-or-death engineering crises. To keep Voyager 2 operational, NASA engineers have been forced to play a high-stakes game of remote hardware management. Over the decades, they turned off the cameras, the infrared sensors, the ultraviolet spectrometers, and the heaters warming individual instruments. The scientific instruments are surviving in temperatures far below their original design specs, frozen solid in the deep dark, yet somehow continuing to record telemetry. Then came a critical mechanical emergency involving the spacecraft's attitude control thrusters. To send data back to Earth, Voyager 2's 12-foot parabolic high-gain dish antenna must remain pointed directly at Earth with incredible precision. If the antenna drifts off target by even a fraction of a single degree, the narrow radio beam misses Earth entirely, and the spacecraft is lost forever. To maintain this alignment, Voyager 2 fires tiny bursts from its hydrazine thrusters, nudging itself back into alignment whenever it drifts. But after decades of operation, microscopic fuel residue began building up inside the thruster lines. Fuel lines were clogging, requiring more pulses to achieve the same corrective maneuvers. If those thrusters failed, Voyager 2 would tumble out of alignment. Working with decades-old paper documentation written in the 1970s, JPL engineers came up with a brilliant fix. They decided to switch Voyager 2 over to a set of backup thrusters that had been dormant for decades. In a high-risk operation across a 39-hour communication delay, they sent the command to activate the backup thrusters. They fired flawlessly, clearing the line and extending the spacecraft's pointing lifetime. Then, another crisis hit in 2023. Power levels dropped so low that NASA faced an agonizing choice: shut down one of the remaining active scientific instruments, or find a way to hack the spacecraft's power management system. Every spacecraft carries built-in safety mechanisms to handle power spikes. Voyager 2 had a voltage regulator connected to a reserve power system designed to protect the electronics if the main power line fluctuated, but that reserve circuit consumed a tiny fraction of electricity just by staying on standby. JPL engineers made a bold decision. They wrote a custom software patch that disabled the onboard voltage safety regulator, redirecting that tiny pocket of reserve power directly into the science instruments. It was a calculated risk. If a power spike occurred, it could fry the spacecraft. But the hack worked. The maneuver bought Voyager 2 years of extra science operations. Most recently, in August 2026, JPL engineers executed an incredible delicate maneuver internally nicknamed the Big Bang. The team simultaneously swapped out multiple power-hungry components aboard Voyager 2 for lower-power alternative devices. The operation required powering off selected legacy subsystems while carefully balancing the thermal levels to prevent the frozen instruments from dying in the near absolute zero environment. Without this Big Bang maneuver, NASA would have been forced to turn off another vital science instrument on Voyager 2 before the end of 2026. Instead, this successful software bypass bought the probe another full year of multi-instrument science. It is easy to view Voyager 2's journey as a purely academic endeavor, a distant probe sending back esoteric numbers from a dark void billions of miles away. But the data Voyager 2 transmitted back from the edge of our solar system has profound implications for the survival of every living creature on planet Earth. Before Voyager 1 and Voyager 2 crossed the heliopause, we had no direct way to measure how effectively our heliosphere shields us. The deep space outside our solar system is perpetually swept by galactic cosmic rays, highly energetic atomic nuclei stripped of their electrons and accelerated to nearly the speed of light by cataclysmic events like supernova explosions and supermassive black holes. If those galactic cosmic rays were to hit Earth unhindered, they would strip away our ozone layer, shower the surface with ionizing radiation, mutate DNA, and render life on Earth nearly impossible. Voyager 2's direct plasma measurements revealed that our heliosphere and the superheated magnetic firewall at the heliopause acts as a massive shield, blocking out roughly 70% of all dangerous galactic cosmic rays. Think about what that actually means for a second. Our sun is not just giving us warmth and daylight. It is carving out an invisible bubble that acts as a planetary radiation shield. We are traveling through a radioactive galactic wasteland inside an armored, solar-powered magnetic spacecraft. Understanding this boundary is also vital for the future of human civilization. As humanity prepares to establish permanent bases on the Moon, build colonies on Mars, and eventually launch crewed missions into interstellar space, we must understand the space weather outside our bubble. Voyager 2 has given us our very first localized in-situ weather report from the interstellar ocean. We now know that interstellar space is not uniform. The heliosphere actually breathes, expanding and contracting in dynamic 11-year cycles as the sun moves between solar minimum and solar maximum. As the solar wind pressure drops, the interstellar medium pushes the heliopause inward. As solar activity flares, the bubble inflates outward. Voyager 2 showed us that the cosmic border is a shifting, living frontline. Today, Voyager 2 continues its silent, solitary journey deeper into interstellar space. It did not stop. It is traveling further from home every single second, covering more than 900 million miles every year. However, the clock is ticking down toward an absolute physical limit. Despite the heroic efforts of engineers at JPL, the plutonium I-238 inside the RTGs is decaying second by second. To manage this inevitable drop in power, NASA has systematically shut down instruments. In September 2024, engineers shut down the plasma science instrument. In March 2025, they turned off the low-energy charged particle instrument to conserve power. Now, in 2026, Voyager 2 is operating on a bare-bones payload, prioritizing its magnetometer and plasma wave subsystem to collect every remaining drop of magnetic field data. By the late 2020s or early 2030s, electrical power will drop below the absolute minimum threshold needed to operate the main radio transmitter. On that day, the final whisper of telemetry from Voyager 2 will travel across the void, taking more than 20 hours to hit the radio dishes of the Deep Space Network. The signal will flicker out, and Voyager 2 will drop into permanent radio silence. Yet silence is not the end of its mission. In the vacuum of interstellar space, there is no atmospheric friction, no water vapor, no oxygen to cause rust, and virtually no dust particles to erode metal. The physical structure of Voyager 2 will remain almost perfectly preserved for hundreds of millions, perhaps billions of years. In roughly 40,000 years, Voyager 2 will drift within 1.7 light-years of the star Ross 248, a red dwarf in the constellation Andromeda. In about 296,000 years, it will pass within a few light-years of Sirius, the brightest star in our night sky. Long after the sun expands into a red giant billions of years from now, long after the oceans of Earth evaporate and the great cities of humanity crumble into dust, Voyager 2 will continue orbiting the center of the Milky Way galaxy, a silent, indestructible monument to a species that dared to look up at the stars and reach out into the dark. Affixed to the side of Voyager 2 is a famous 12-inch gold-plated copper phonograph disc, the Golden Record. It contains 115 images encoding the story of Earth, diagrams of DNA, images of human anatomy, landscapes, animals, architecture, and scientific equations. It holds spoken greetings in 55 human languages, the sounds of humpback whales, the sound of rain, footsteps, a mother's kiss, and brainwaves recorded while thinking of love. It carries music spanning cultures and eras: Mozart, Bach, Beethoven, Indonesian gamelan music, Navajo night chants, and Chuck Berry's Johnny B. Goode. When NASA launched Voyager 2, scientists thought they were sending a simple planetary probe to collect data about gas giants. They thought they were asking basic questions about celestial mechanics. In reality, Voyager 2 taught us something far deeper about our place in the cosmos. It proved that human curiosity is not bound by the gravitational pull of our home planet. It showed us that a tiny machine, built with technology that is primitive by modern standards, can cross billions of miles of dark vacuum, punch through a superheated cosmic wall, and redefine our understanding of the universe. We live on a fragile blue marble suspended in a vast, dark, radioactive ocean. Yet we have built something that will outlast our planet, outlast our star, and perhaps outlast our entire civilization. Voyager 2 is out there right now, cold, silent, and flying at 34,000 miles per hour through the interstellar dark, carrying the memory of who we were, what we felt, and how far we reached. What do you think about Voyager 2's incredible journey into the interstellar ocean? Does knowing that a piece of human history will outlast our solar system change how you view our place in the universe? Let me know your thoughts in the comments below. Thanks for watching, and stay curious.